All right, other questions? Anything else about comparable or comparator? Comparable, if you're going to overload the compare to. Comparator, if you're going to define a bunch of different classes, each of which have a compare method in them. Each of those compares can then be used when you instantiate those objects to sort things via that logic. So you can swap those out at runtime. And you can see how the way that what I mean by during runtime is we specify it in this driver or main class. We specify the behavior that we want and we swap in the associated compare, and it's not locked in like it would be with comparable. There's only one overridden compare to that tells us how to compare the objects. We can't swap them out and do different things in a single program like we could like this. And in fact, you could do something like query the user. Would you like to sort by 1, 2, or 3? And they could type a certain thing. You could read in that thing and then swap in the associated compare that you wanted to. So the user could define how they want to compare objects. You just define all of the different ways they can compare objects, and then they get the choice of how they want to do it. All right. No other questions? We'll move on to encapsulation. Does anyone want to tell me their best guess or their best to the best knowledge? What does encapsulation mean? What is it? Yeah.
Is it protecting the fields and also the other stuff from the user so they cannot change it?
Yeah, and it may even be other objects. Some objects just shouldn't have read-write access to other objects, and certainly the client, whomever is sitting using the objects that you've made, you don't want them messing with the internal representation of the object. My go-to example for this is your GPA. Maybe I have access to your degree audit. Should I be able to change your GPA because I want to? That seems a little bit like abuse of power, right? Just a little bit. I should not have the ability to do that. It's not an editable field. No one else should be able to make those modifications. They should adhere to the specific rules of exactly how a GPA is changed. When you get a grade at the end of a quarter, then there's a specific calculation that needs to happen based on the number of credits that you've earned and the grade that you got in that class, and your GPA updates in exactly that prescribed way. Any other change to that, any other way to access that, and you end up with something that is, it's a security vulnerability. So encapsulation, we need to know that fields are always private. If you want to be able to read or write a field, you need to have a getter or a setter for that field. That allows you full creative method-based control over how that happens. You can give them full read-write access by just making a generic getter and setter, but if you want to reduce the logic for this to make sure that it's only changed in specific ways, you can add that logic to your getter or to your setter, and then only at certain times are you able to read from a particular field, or only at certain times are you able to write in particular values to those fields. So getter methods are public. You want to make sure that your objects can't be modified by anything outside of them. This helps also hide the internal details of your objects. I'll probably go back to this a few times throughout the quarter, but who here 100% knows exactly how the internals of your car work? All of it, down to every detail. Do you need to know this in order to operate your vehicle? How much harder would driver's ed be if you needed to know every little detail about your car in order to pass your driver's test or in order to operate your vehicle? The basic idea is that we can use objects without fully understanding the internal details of them just because they've been designed such that the interfaces to them are more accessible. The user interface in your car tells you what's important from a driver's perspective. It tells you the engine temperature, it tells you the current speed that you are going, it tells you the level of gas that you have in your automobile. You don't need to know more than that in order to understand the internal representation of your car. If there's another bigger issue, then you can either go diagnose it yourself if you understand it, or you can take it to somebody else. But on a day-to-day, minute-to-minute basis, you don't need more information than what is described for you in the user interface of your automobile. The exact same thing happens with code. When you make a scanner object, do you know exactly what's happening underneath the hood with that scanner object? Do you need to? You really don't. In order to use a scanner, you just need to know what are the methods, what can I do with a scanner, how do I make those connections? Great. Let the internal details handle themselves. Someone else thought of it, someone else checked it, it's going to work. Great. It's exactly like driving a car. So what this allows you to do is give the programmer, the person who's actually making this object, full control over how others are going to interface with your code. The people who wrote the scanner decided exactly what the programmer should and should not be allowed to do. You cannot mess with the underlying representation of the scanner. In fact, you may not even know the underlying representation of the scanner. What fields are in a scanner object? What methods are in a scanner object that are private that you can't call directly? You don't know, but it's outside of the necessary knowledge that you have. They have determined what level of read-write access you need in order to manipulate a scanner object for your benefit, hiding the unnecessary details in the code to just make it work. So I already gave you the car example. You have specific tools that you use to interact with the car. You have pedals, you have a gear shift if it's a manual, you have a steering wheel. They do specific pre-described things that you cannot modify. Without knowing exactly how a car works, you can't press the gas and make that brake. So you have no more control over your car other than what your inputs can control. So taking this and bringing it back to code design, when you're thinking about and making your own objects, you want to think about how do all of the internals work? Because as the designer, you need to know how all those details work. You've been using a lot of tools as a user, but as you start moving from being a user to being a designer, you need to start thinking about, you're going to be the mechanic who constructs the car, the engineer who constructs the car, and not just a driver of the car. So you need to think about absolutely everything about the underlying details. So you need to know how all the internals work of all of your objects. Then you need to think about, from the driver's perspective, from someone who's going to be using this object, what should they be able to see? What should they be able to modify? Then your next task is to design the tools, design the methods for how you're going to interact with how someone else is going to interact with your object, using the appropriate level of control when they have an instantiation of the object that you've made. So that's the basic idea of encapsulation, is that the user should only have the level of control that they need to operate the object. They don't need to understand all of the details. And in fact, they shouldn't have the ability to make changes to the internal details. You don't want a 4-year-old messing with your car. They don't know what they're doing. In general, when you're designing something, assume that the end user is the dumbest person you have ever met. If you give them the power to mess something up, they will. Questions about encapsulation? All right, inheritance. What is inheritance? Who wants to give me some kind of overview?
I think it's like when you have like a main class like a car class, for instance, and I think when you have like other subclasses,
Mm-hmm.
like you have truck, SUV, whatever, for instance, they can like inherit from that main method. And
Yeah.
take that.
Exactly. What's the purpose? Why do we care about it? That is exactly right.
Just makes it, you don't have to rewrite everything.
Yes, that's the main code reuse. Computer scientists are the laziest people I have ever met, myself included. If we don't have to do extra work, we don't want to do extra work. We're going to make tools that make it easier for us to design things so we don't have to do things over and over and over and over again. You make a computer scientist do too many repetitive tasks, they give up and go away. I can't tell you how many math classes I've been in where they give you a 40 problem set and you understand the idea by the fourth problem and you have 36 more of them to go. It just makes you want to rage and rip up the entire assignment, right? That sound familiar? So inheritance, we're going to call this an is-a relationship, hopefully going back to some of the terminology that you saw in 211 between two objects. We have something like an SUV is a car. A car is a generic term that can represent any number of different subtypes of automobile. Could be an SUV, it could be a van, it could be a passenger car. So we have what we call either the base class or the parent class. And then we have a derived class or a child class. We use the keyword extends if we're going to be extending another class, or implements if we're going to be implementing an interface. Does anyone want to give me a difference between a class or maybe even an abstract class and an interface? What's the difference between those two things?
I think with the class you can extend, but with the interface you can implement.
Yes, so the keyword definitely differs between those two, absolutely. What other differences are there between those things?
This kind of guess, but I think
Yeah.
with the abstract, you have to implement every, like, whatever it calls, whatever it has in there, it has to be referenced in some way, fashion.
That's a very good idea. So let's talk about this in a little bit more detail, because I think this is a very important distinction, that these become tools in your tool belt that you can use whenever you need to. So an interface has absolutely no implementation whatsoever. You are not allowed to write any code in an interface. All you can do is define, here's what the method header looks like. So you have something like, before we had the add function, you would have int add, int A, int B, done. There's no logic about how that's going to be done. You just say that in order to make one of these kinds of objects, you must give me a definition for how to add two things. So no implementation whatsoever. With an abstract class, you can implement as much as you want, but to be an abstract class, at least one thing must be not implemented. And this is useful in an inheritance hierarchy because maybe all cars can do something together, but the way that they do those things are slightly different. So for instance, there might be a method called drive. And the way that drive works in a manual automobile versus an automatic automobile is slightly different. You have to worry about a clutch and a gear shift. You can't just shift into drive and go in a manual. So the child classes of this car object will have to further define what drive means. So between both of these, We cannot instantiate either one of them, because in order to make one of these, you need to have all of these implementations figured out. When I say go drive it, there needs to be exact logic for how to drive it. There cannot be any ambiguity. The example that I like to use for this is something like, if I asked all of you, draw a car. Make sure that you have things like the make of that car, the model of that car. I'm not gonna specify what it is, I'm just gonna say draw a car, but the car needs to have all of that associated information. Is there the ability for two different people to draw two different cars? And the answer is yes. So because of this, you cannot instantiate an abstract class because at least one of the methods hasn't been defined. We don't know whether it's a truck or an SUV or a passenger car or a van. We just don't know. So because of that, there exists ambiguity. We cannot make a car. We can't just take a base car class and say make one of these because it's not defined what it is yet fully. But in an abstract class, we can define anything that is shared in common between its children, between its those that inherit from it. Does that make sense? And child classes. The other major difference between an interface and an abstract class, a child class can implement any number of interfaces, but a child class of any other inheritance hierarchy, it could be abstract or not, you can only extend a single class. And note this is a Java-specific thing. In other programming languages, you can actually extend multiple classes, and later on this quarter, I will talk about what that looks like in those other languages and what issues you have to consider if your programming language allows you what's called multiple inheritance. But Java allows only singular inheritance. You can only extend from a single class. Questions about the difference between interfaces and abstract classes? Hopefully that makes a little bit more sense. Any questions that I can answer about them? Yeah,
Abstract class, is that like using extends or is it like?
yeah, I guess I should also include it's kind of the differences right here. You use the keyword implements for interfaces and use the keyword extends for abstract classes. So given some examples of this, we find that base classes or parent classes are often abstract. We see this a lot because we just don't have enough information. And we want to, as computer scientists, factor as much of the common code between all of these child classes. We don't want to copy and paste. In fact, it's horrible code design to copy and paste code. If you find yourself ever doing it, there's a better way. So the goal is to know what those better ways are so that you can create code that is easier, simpler, more extendable. That is the entire purpose of this class, is to figure out what are the tools that you have that you can add to your tool belt that help you to be able to create code that is that's easier to modify in the future. And if you find yourself copying and pasting, if you ever have to make changes to one of those things, you have to figure out how many places did I paste this code? You need to make that change in all of those places. If you miss one, your code's going to break. It's a nightmare. So these child classes, they only need to specify information that is different from that is defined in the abstract or base classes. So if you abstract as much as is shared in common between all of those objects into those parent classes, all you have to do is talk about what differs between a truck and a van and a passenger car and an SUV. Questions about inheritance? Polymorphism. What is it? Did we see this in 211? Yeah.
I think it was, same code, two different things, many different ways of doing things with the same code.
Yeah, so it's important to have an understanding of inheritance before we go into polymorphism, because you can actually instantiate things that may change at runtime as the base class. And we will figure out as the code runs, which one of its child classes are we actually referring to. So as you write the code, you can use the interface or the abstract class in place of some derived class. And then when someone during runtime specifies which derived class they want, then you have generic code that can work for any of those particular subclasses, any of the choices that they have. So you can instantiate a truck as a car rather than an actual truck. And then you can, at runtime, fill in the gaps of what a car is. And that way you can make a car array where the first element is a truck, the second element is an SUV, the third element is a van. And you can shove them in the same objects because we have the base representation of, we have a list of car objects. What each one is one of its derived classes. But you don't just now have to make a truck array or an SUV array or something else. You can use a car array, and any subclass of car can now be filled in any of those components and mixed and matched. So we know objects in Java are already of multiple forms because we don't actually have to specify this. Every class that we write by default extends the object class. And object is just the most generic thing that exists in Java. In fact, I very much don't like it when people use the word thing, but it is the most specific thing that you can say about the object class. What is an object? It's a thing. It's generic by default. It is the most generic thing that you could have. Every object that exists in Java is derived from object. So we need to talk about the two different kinds of polymorphism that we care about. The first one is compile time, and the second is runtime. But compile time, polymorphism, an example of this is method overloading. We just talked about having the add function and having a bunch of different parameters lists that we could have for that. That's an example of polymorphism. When you say, I want to call the add method or the add function, then which one do you call? We don't know until we have some kind of compile time analysis that goes and says, how many parameters are there to this? What are their associated data types? Now I know which method to call, even though there was ambiguity about them. So that is compile time polymorphism. So that's static. There's also dynamic, which is more type-based. So we have a superclass, we have a subclass in an inheritance hierarchy. They have implementations of the same method that have exactly the same signature. There's no way to know this at compile time. There's no way for the compiler to go figure out which method you're trying to call. So we have three different options for dynamic polymorphism. We can have the superclass referenced as the superclass. So in this case, car is not abstract. So we could say car equals new car. And as long as we can actually instantiate it, it's not abstract, then it's the superclass referred to as the superclass. We can have the subclass referred to as the subclass. So now we would have something like SUV equals new SUV. But then we could have the subclass referred to as the superclass. So here we would have car equals, or car SUV equals new SUV. We can shove an SUV into a car-shaped hole because any subclass of that can be referenced by its superclass. So that was the concept of, so we have superclass object equals new superclass. We can only use those as they're defined in the superclass. And then as the program is actually running, we figure out which of the subclasses methods we're going to be calling. So if it's a car, then we figure out if it's been instantiated as an SUV, then we refer to the SUV class and its associated code to get rid of the ambiguity of, let's say we wanted to call drive on this car object. If we instantiated it as an SUV, then we use the SUV's drive method rather than the truck's drive method or any other potential subclasses method, drive method. That make sense? Does that seem mostly like what you learned or saw in 211, hopefully? Questions about polymorphism? We will see it a lot more throughout the quarter. Composition. What is composition? I know that 211 probably made a bit of a difference between aggregation and composition. I'm kind of looping them or grouping them together for now. We'll actually talk about their differences a bit later. But generically, what do we mean by aggregation / composition? What kind of relationship is it?
If polymorphism is a relationship, this might be more of a has of a relationship.
It is, exactly. And as a has a relationship, this is what happens when we compose another object out of sub-object components. So whenever you have an object, there's no way to actually instantiate this kind of object. It eventually has to break down into the primitive components of Java. So ints or doubles or chars, basically that, one of those things. So maybe we have a person object. And a person is made up of a string name and an int age and a, I don't know. Trying to come up with some other object, a clothes array for the kinds of clothes that this person has on. Random off the top of my head idea. But eventually this is all going to break down into basic types. So a string breaks down into an array of characters. An int is already a primitive, but if you were to look at the clothes implementation, this would break down further into another object, a clothes object that would eventually break down into maybe there's an int here for the number of them. You have 2 socks, you have 1 shirt, etc. An int and some other components that eventually break down into primitives. So composition is has a relationship between 2 objects that allows you to define objects in terms of other objects. What this means is that the higher level object like this is more abstract because it's made up of other components. But eventually those components all have to break down into something that the computer can store. We have definitions for how to store integers and doubles and characters. We don't have internal representations for how to store persons. This has to be defined, and it has to be defined out of objects that already exist and are defined, or primitives. And that allows us to just get more and more and more abstract as we allow more and more composition. So the basic idea, an object can be made up of other objects. So its fields can also be objects. All right. Between inheritance and composition, all things equal, which one should you choose? What do we think? Any guesses? Let's say you could implement the same thing two different ways, one via composition, one via inheritance. Yeah,
Inheritance.
inheritance? Who thinks inheritance? Who thinks composition? The one person who said composition is correct. And we're gonna see this as we start to look into design patterns, because more of them are going to use composition than inheritance. In fact, inheritance is gonna have a significant number of flaws associated with it as we start to scale the size of what we're trying to do. Inheritance gets to be a huge pain when things grow. You have an expanding number of subclasses. Whenever you want to make a single change in something, you have to make it in all of those associated subclasses, and it becomes an absolute nightmare to maintain. On the other hand, if you have composition, the change is embedded in the object, and each instantiation of those subclasses are all going to refer to the same object. So you make the change in one place, and it will branch out to all of the places that you want. So the first general rule that you're going to want, we're going to come up with a bunch of general rules throughout the course. But the first one is, whenever things are equal, choose composition over inheritance. There are reasons to choose inheritance over composition, but they are kind of fewer and farther between. It's an excellent tool to have in your belt. Inheritance is a necessary part of computer science. It's only when all things are equal, the extendability of your code will be increased by choosing composition over inheritance. Speaking of principles, we're going to speak to a few of them now. I'm just going to kind of define them, and we'll come back to a lot of these as we start talking about design patterns where these matter. So the first one is to encapsulate what varies. If you have something that changes between different objects, we want to make sure that outside of that object, that change can't happen. The change needs to be defined within the object that's responsible for that change. If you don't have that, it becomes an absolute nightmare to maintain. Next one is the one that we just talked about, favor composition over inheritance. Talk a little bit as to why that was. Where possible, you want to program to an interface rather than an implementation. So if you can move stuff up the inheritance hierarchy into an interface and have all of that information in the interface, then you want to make sure all of your derived classes focus on implementing that interface. You don't want to make too many changes that are not in the interface in your classes, because again, that will become a huge pain to maintain. It doesn't super matter that you write all of these down or understand them fully now. I just kind of want to go over in general. We'll come back to them in a bit. We want loosely coupled designs between objects that interact. And what we mean by that is if they're loosely coupled, that means there's not a ton of communication happening between them. That means that this object doesn't really affect that object very much. This object doesn't really affect that object very much. We have them such that if you make changes to this object doesn't also need to be changed. If we change this object doesn't need to be changed. If we do that, then we can make free changes to both objects and not break our code. Of course, if they interact, we want to minimize the number of ways and places that they do interact so that when change is necessary, there's just less work for us to do. Next, classes should be open for extension, but closed for modification. This means that if we want to add something to a class, that should be doable. We want to be able to add functionality to a class. So we need to design our classes such that we can easily do this. On the other hand, we don't want our classes to be able to be changed. If something changes and the requirements change, The actual change that we need to make should not be going and editing our code. It should be doing something like creating a new object and plugging it in its place. Or something that allows us to swap things in and out, rather than having to go make those editing changes to our code. That introduces a ton of bugs, and in complicated programs, you have lots of different interactions. If you change what you think is a small isolated component, and it's not actually a small isolated component, you will break something else, and then you need to go modify that, and that breaks 3 other things, and you need to go fix each one of those things, and you get an exponential complexity of the things that you need to fix, and you end up with spaghetti code that you use to fix the issues that arose when you tried to modify the object. It's just something that I've experienced over and over and over as I've designed things myself. It becomes a logistical nightmare to try to make all of those changes and to make everything work at the end in a nice, clear, concise, easy to read way. On the other hand, if you think about the design in advance and think about the extendability and the lack of modification of your objects, then when modification is necessary, then it's much easier to do that in a way that does not break the rest of your code. Next, depend on abstractions. We don't want to depend on concrete classes. Wherever possible, we want to utilize interfaces and abstract classes in our code. We don't want to be using concrete classes. We want to refer to things by their abstractions and then filter down into the concrete classes rather than referring directly to the associated concrete class, because then we need a bunch of different logic for each of the different concrete classes. Whereas if you can use polymorphism, refer to the abstract class, and then figure out from there, what do I call? It's going to be a lot less work. Only talk to your friends. Objects should only be communicating with objects that are in the same package or immediately related to them. You don't want to be communicating with objects that have nothing to do with this object. It's easier to make a call chain that goes through related objects than just bypasses that entirely and goes off to some object that does something else. Don't have some other object request things. We're going to request things of other objects. And a class should have only one reason to change. So if we're going to modify something, keep that to a single instance where possible. These principles are not always possible to follow on an instance by instance basis. They're more principles. If you can adhere to them, you should adhere to them. There will be times and places where it does not make sense to adhere to them, and we'll talk about how to identify those situations later on in the course. We're out of time. If you have any questions, let me know. I'll stick around for a few minutes. Other than that, I will see you tomorrow.
And we're late parking. I had trouble finding like what is speed parking? Really, speed parking is a bit hard to find. You have a
Yes. It is up on campus.
You don't have a.
I do not have a paper version, but I can print you out one.
Okay, that's what Thanks. And you have your slides on Canvas, right?
They will be up as soon as I finish them. If you'd like to have them in advance, I can add you to the repository of slides so that you can print them out or.
Like just what access to online really.
Sure, yeah, they will absolutely be on Canvas before any kind of exam or anything of the sort.
Okay.
But if you'd like them in class as I'm going over them, I can work with that too.
Like as long as like if it's also on Canvas, I can access it well. I'm happy.
Yeah, if you were looking for them and something isn't up on Canvas, send me an email and I'll get them up as soon as I
Okay,
can.
thanks.
Yeah.
Out of curiosity, for the collection, but so were you able to pass in the function pointer for the